Swayam Prabha. Digital India. Educated India.
Okay, good morning everyone. So we're going to continue with the hydrogen embrittlement part. I think you may remember that it says here that I'm muted, but it's not a problem. You can hear me? You can hear me well, right? Or is, okay, it says something about muted or something, but it's fine. Okay, yeah, so we're going to continue with the hydrogen embrittlement part. I said a few things, not only about hydrogen embrittlement, but if you remember yesterday in the last session, we were saying that how can it possibly be that sometimes we see brittle failure in metals when we know that in order to break one of those brittle interfaces, we need stresses around the order of 10 times the yield stress, 9 times the yield stress, and we don't see that when the moment we bring plasticity in, dislocation emission lowers our stresses, and we know that, I think I plotted some stress field there, we get a stresses at maximum that are 4 or 5 times your yield stress depending on your hardening. So how can we make up with this for this change? So I'll discuss a little bit of that and then connect again with hydrogen embrittlement and discuss a few examples of phase field modeling and hydrogen embrittlement that I have not discussed so far. So yeah, that's about it. That will be 1 hour and a half, more or less. We'll do a coffee break, and then I get into multi-physics phase field modeling. I will explain in general how you model coupled problems in phase field. I will particularize this to the case of abacus, and then tomorrow we'll have corrosion and battery degradation. And as usual, interrupt me anytime. Just raise your hand when you have any questions, and I'll do a break. Yeah, 45 past or so, just a 5-minute break. Okay, so this is the idea, basically. Okay, how can we rationalize cleavage fracture in the presence of plasticity? And this is something that we have seen often. It's not the default mode of failure of metals. Metals fail normally in a ductile way. You know, it boils to nucleate, to grow, and coalescence for a metal to fail. However, on occasion, we do see these brittle interfaces rupturing in the presence of significant plasticity. And we wonder why this is the case, because our understanding is that stresses are not large enough, so something must happen. And this is something that has been reported. All these experiments have something funny about them. They're not typical experiments. If you do a typical experiment on a metal in air, you get a ductile fracture process. So there's something happening there. And the question why we don't understand it is because atomic decohesion requires traction level stresses on the order of the theoretical lattice strength, so around 10 times the yield stress. And we know that in conventional stresses, in conventional plasticity, if you take von Mises plasticity, for example, the stresses are bounded at around 3 times the yield stress. Depends a little bit on the hardening. So this is the very first finite element paper on large strain plasticity, looking at the crack tips. This was done by Mock McMeeking in the 70s. He was a student of Jim Rice at Brown back then. And you can see what he's plotting here is the solid lines are the stresses, the crack tip stresses. Normalized is the hoop stress, so it's the stresses ahead of the crack tip. You can think of only, you can focus on the theta equals 0, so it's a polar coordinate system, so theta equals 0 is the extended plane along the crack line. And this is the sigma 0 means the yield stress, the initial yield stress of the material. And he's running these calculations for a given ratio between sigma 0 and Young's modulus, which is very sensible. He's looking at multiple directions. This is the crack tip. You see the polar coordinates here. It's an old paper, you can see. And on the dashed lines are the plastic strains. So of course plastic strains increase very significantly. This is, by the way, for a material that has no strain hardening exponent. So perfectly plastic material. And you can see that the maximum stress that he gets is, of course, along the theta equal to 0 direction, and is 3 times the yield stress. So it can be higher. It can be 4 or 5 times the yield stress, depending on your strain hardening exponent. But this is very far away from this 10 times yield stress. So this is something that we don't understand. How can it be that this interface ruptured when we have this situation there, where stresses are not large enough? So this is the idea, basically. This is your crack. This is your tensile stress ahead of the crack tip. This is the distance ahead of the crack tip. Your stresses look something like this. This is kind of a sketch of what you see here. But in order for brittle fracture to occur, we need stresses on the order of 10 times the yield stress. And I should emphasize here that I'm discussing these fracture mechanisms in the context of the stresses. But in reality, as you know, fracture occurs due to an energy, right? Energy absorbed versus energy propagation. Otherwise, we'd have fracture at very low loads in linear elastic materials. So what I mean, you need to hit this stress. Not only you need stresses that are big enough to nucleate a crack, but the stresses need to be big enough over a sufficiently long distance. At the end, energy is stress over a distance. So your stress needs to be sufficiently long over a long distance, such that eventually you get enough energy to rupture this grain boundary or whatever cleavage plane you're interested in. So basically, this is the problem with metal, right? So if you start loading a metal, maybe I can draw it in a sketch here. I don't know if I have it in the slides. I don't remember right now, so I'm going to draw it. So if I have my crack, this is the distance ahead of my crack. This is my tensile stress. Yeah, if we think of stresses as energy as stresses over a distance, in order for cleavage fracture to occur, you have this thing that is 10 times the yield stress. And you need the stresses to occur over a sufficiently long distance, let's say this distance. So when you start loading a metal, initially your stress looks something like, I don't know, this is your yield stress. Your stress goes up, eventually you hit your yield stress, and then depending on your hardening, you do something like this. You keep increasing your stresses, and then according to conventional plasticity, you start doing things like this. So you never really, the peak, I don't know if you've seen that in fracture mechanics courses, but the peak of your maximum stresses moves away from the crack tip, but it stabilizes at a certain limit. So you never really get any close to this. And not only you need to hit this spot, you need to hit this spot over a sufficiently long distance. So that's why eventually other things happen. More plastic strains-driven failure mechanisms take place, like void coalescence and void growth and coalescence. This is the issue. So this is when it's quite common, I think, used in the automotive industry. Sometimes they look at cleavage versus ductile fracture, and they have basically rather simple models which are based on a principal stress if you have some sort of cleavage fracture, or an equivalent plastic strain if it's based on some ductile fracture mechanism. So this is what happens. Okay, so how can we explain this? What are we missing here? What is missing in our picture? What is continuum mechanics not telling us? So what continuum mechanics is not telling us, or the other thing that we learn through experiments, is that metals have a size effect. You can see this is a classic set. I mean, it has been shown across a very wide range of experiments: microbending, microtorsion, indentation, and many, many others. Some sort of shear loading of micropillar compression. But what you see here is the more striking experiments, the ones that I like the most. So these were experiments done by Fleck, Muller, Ashby, and Hutchinson some years ago, and they were looking at thin copper wires. And you can see that they loaded those thin copper wires, they're very thin copper wires, and they're both tension and torsion. And you can see that in tension, in both cases they're plotting equivalent quantities, right? So this is stress versus strain, and in torsion you're normalizing the torque by the diameter, so you have an equivalent stress, so to say, and a strain, rotation, that is, the kappa by the diameter. So these are all normalized, which means that there's no sample dimension in there. Both are kind of stress-strain curves. And stress-strain curves, of course, are not depending on the geometry of the material, otherwise we couldn't use the output of a uniaxial tension test to see what happens in a bridge. And this is what you see when you do the uniaxial tension test on the wires. You see that all the curves fall on top of each other, more or less. There's a little bit of a scatter, but it doesn't really follow any order, right? So the 12 is between the 15 and the 20, so it's not really, becoming. There may be a little bit of an effect of the microstructure, but more or less is what we expect. We get quite good reproducibility. We make our wires thinner or thicker, and the response is more or less the same. So this is what we expected. This is why we have hardening laws that have no size. When we develop a hardening law, we don't think of any size of the sample. We just say, the stress is like this, and then it looks like that. That's all we need. However, in torsion, in this equivalent, again, I emphasize, these are equivalent normalized stress versus strain curves, we see that thinner wires are much stronger than thicker wires. You see this is a very thick wire, not very thick, but relatively thick wire, and you can see that you're much, much stronger. Thinner wires are much stronger than thicker wires. And this is puzzling, because if you take any other plasticity model, if you do this experiment, in Abacus with von Mises plasticity, and you do your simulations and you normalize your torque by your diameter, you'll get always the same curve, because it's a stress-strain curve, right? So it doesn't matter which size of sample you take, you are dividing force divided by area, so you are getting always the same curve. You're changing your area, but because you're dividing by area, you get always the same curve. So something's happening here. And what was interesting is that what these experiments very clearly reveal, and people have seen this in microbending. So I think this was the interest in microscale behavior came up with microelectronics. So there was a lot of interest, companies like Intel trying to understand microelectronics, and therefore there was an interest on this kind of gradient plasticity models. But basically the idea is that what you see very clearly here is that the only difference between this test and this test is that in uniaxial tension, the strains are uniform. You have the strains, there's no gradients of plastic deformation. All the strains are the same. While here, you have gradients of plastic deformation in torsion. So the idea is that whenever you have gradients of plastic deformation, you have something that brings this size dependency that we don't see for either larger samples or uniform strains. And what happens basically is that this is related to geometrically necessary dislocations. This was a concept that we know since many years ago. I think Ashby started discussing this in maybe even as early as the 70s. And the idea is that whenever you need to, if you imagine, for example, a crystal lattice under bending, you need to accommodate some extra dislocations in that crystal lattice, and those are what we call geometrically necessary dislocations. And normally these geometrically necessary dislocations, GNDs, they don't play a big role in big samples, but in the small samples, they kind of act as obstacles to plastic deformation, and they lead to this additional strengthening. So a lot of people, a lot of very good mechanicians, so you can see some of the names there, decided to spend their efforts in trying to extend this conventional plasticity models to account for the size effect, to be able to capture the size effect. And the way you do that is typically in two ways. You either extend your plastic work to make it not only a function, if you think of your equivalent plastic strain, not only a function of your plastic strains, but also of your plastic strain gradients, which appear in the torsion thing. Or you can define your flow stress, not only a function of the plastic strain, as you normally do, but also a function of the plastic strain gradients. And of course, the moment you bring a gradient into the picture, it's derivative with respect to space. In order to get dimensional consistency, you need to bring a length scale. So you need to multiply these things by a length scale. So you see here, derivative with something that has no dimensions over distance is 1 divided by meter, so you need a meter there. So then this length scale is what allows you to capture the fact that you may have in your sample a gradient over a small length scale. And when you do that, as you can see here, this is a prediction with this. These models are called the strain gradient plasticity models. When you take these strain gradient plasticity models, you can see that you're able to capture very nicely. This is a finite element modeling of this experiment. Again, if you do it with conventional plasticity, you will get always the same result. But if you do it with a strain gradient plasticity, you see that you get exactly what you see in the experiments. So a very good agreement with experiments. So then what is the meaning of this length scale? Well, it's in a way you can think of it as a strain hardening exponent, so to say, right? It's a measure of how much a material hardens, develop GNDs for a given set of plastic strain gradients. This is more or less the idea. But this is something that appears at the macro scale and that we are missing in our models. And this is important as well in fracture mechanics, even if we think about big samples. So forget about the macro scale samples anymore, because, for example, this you also see it in micro indentation. And you see it in both ways when you either have, you are doing this indentations over small regions, but also because in indentation, even if you are dealing with a big sample, the plastics are small. So you see some different hardness as a function of the penetration depth. This is a well-known observation. And indentation, if you think about it, is very similar to fracture, right? What happens in fracture typically is that you have a plastic zone that is very small, where your gradients of plastic deformation are going to be very large. So if I go back to those results of McMeeking, look at my plastic strains. My gradients of plastic deformation are gigantic here. So this is the issue, basically. You don't have anymore a microscale sample, but what matters is not the size of the sample, is the size of the gradient, basically. How big your gradient is within what size. And this is what we see in indentation. In indentation, you may be indenting something that is very big. You could be indenting this table, but you see a size effect because your plastic zone is small, so you're going to have a gradient in plastic deformation. So this is exactly what you have ahead of a crack. And it depends a little bit on, and you can see already where we're going, it depends a little bit on how big your plastic zone is. So we were discussing here what happens with as you keep loading and loading and loading, you see as you keep loading, your plastic zone becomes big and big and big. So eventually if your plastic zone becomes very large, then these gradient terms are going to be small. And these gradient plasticity models will automatically capture that, right? Because if there's no gradient, if this term is small, then this flow stress will not be elevated by the gradient term. So the L is a constant. This is a material parameter that you basically fit to an experiment. So for example, you take your favorite gradient plasticity model in the same way that you will take a Holomon power law and you'll fit your strain hardening exponent. Here for your given material, you do a microscale experiment like this one. You take your favorite gradient plasticity model and then you fit the length scale and you get maybe, typical values are between 1 and 10 microns. I think most metals, most alloys will be something like 5 microns, 3 microns, something like this.
So length is geometry dependent.
No. So the geometry dependence is a material property, so it cannot be geometry dependent. The geometry dependency will be captured by this term, by the gradient of plastic strain. So as you change if you model the simulation of the wires, as you make your wires thinner and thinner, then you get different gradients of plastic strain, and therefore this term becomes bigger or smaller. That's the idea. Yeah, exactly. But the length scale is a measure of how, for a given gradient, how much GNDs, how much extra hardening, extra strengthening will come for that material. So basically dislocation activity.
But your L, our material property itself will change, right, at that length scale? Like
with plastic deformation. So some theories include a change of length scale with plastic deformation, but I think it's easy to understand if you think of a constant value. And by the way, of course, this is a plastic length scale. It's not related to the phase field length scale, just to clarify. Yeah, so it's better to think of it as a material property, like a strain hardening exponent. So a strain hardening exponent will characterize how these locations interact and lead to hardening. This will be something that you fit to an experiment, like you fit a strain hardening exponent. I will tell you how, at the microscale, or when gradients are large relative to your sample size, how hardening behavior will occur due to these locations, these GNDs. That's the idea. Yeah.
So that's a constant, right, for a given material?
Yes, exactly.
So once you fit those curves, then irrespective of what size of model I take to load, that remains constant.
Exactly. So then, for example, if you were to work with copper, you will fit this value. I think it depends on your particular theory that you pick, but let's say 3 microns. You fit this value, you run this experiment, you get a good fit, of course, because you did, and then you do a microbending test, and you see that 3 microns captures as well the size effect, and then you do tests on large samples, and you think that nothing happens because this in large samples this washes out. Basically, this is the idea. So it captures this kind of extra hardening that we normally don't have in conventional models. And this, again, the point to emphasize is that we see this very nicely in microscale experiments, but we also see it in indentation. And you may be indenting something that is very large, your sample might be very large, but your plastic zone is small, and what matters is what is the size of your plastic zone. So that's important, of course, in fracture, because in fracture, particularly if you have fracture happening at low applied load levels, you're going to have a plastic zone that is small, so you're going to have those gradient effects there. And in fact, we do see that. So because GNDs are related to lattice rotations, we can do EBSD measurements, and it's very common these days to see that GND densities are very, very large near cracks and other stress concentrators. This is what you see here. This is an EBSD measurement. So what happens in plasticity, if you take one of these theories, and you pick a value that is typical, so you fit to a microscale experiment, and then you simulate what happens inside of a crack, you see something like this. So if you take a conventional von Mises plasticity, it's the dashed line, and the blue line is one of those strain gradient plasticity models. And you see that far away from the crack tip, both things are the same. Plasticity is big enough, widespread, or you have even elasticity at some point. That's not an issue. But as you approach the crack tip, you have these big gradients in plastic deformation. You see it here, right? So here, the gradient in plastic deformation is very small, so not much of hardening effects. But in this area, look at these gradients of plastic deformation. They're going to be very, very large over a smaller area. So those GNDs that appear, that you see very nicely when you do the microtorsion experiments, are going to appear here as well. So this is what you see. You see that the stresses go quite high, but they only go high over a distance that is typically scaling with the length scale more or less, right? So you see this is 2, 3, 4, 5 microns. Yeah, so into more or less the length scale value, you don't have much of an effect. So it's an important effect, but it's an important effect over a very small scale. So then you need to wonder, okay, if I think of a microvoid fracture process, this is a process that occurs at very large applied load, so very large stress intensity factors. Is the toughness of my material is hundreds of megapascals square meter. So this happens over very large plastic zones. And so there is not going to be such an issue. We're going to be somewhere here. That's not a problem. But it may be that you have other problems where this thing matters. So we decided to look into this, whether this could explain this idea.
So in case of ductile materials, generally we can see zones of localized strains. They call it strain localization bands.
Mm-hmm.
And generally within those bands, strain gradients are very high.
Yeah.
And the width of those bands generally tends to be in some microns. So is this length scale in some way related to the width of those bands?
It's a good question. So I've seen people using these models to understand. In fact, the very first models developed on these gradient plasticity models were developed by Elias Saifantis, and he was aiming to precisely explain that. He was trying to understand how the shear band localization takes place, and he decided to incorporate these gradient models to determine that length scale in there. So you could have GNDs, and anywhere you are localizing your behavior, you have GNDs. Whether they play a role depends on how sharp those gradients are, over what distance they span, and so on. But I've seen quite a lot of people modeling that with this model, so probably there's an interest. I haven't looked into myself, but probably there's an interest in explaining this area of localization based on this kind of phenomena. Yeah. So we decided to look into whether these theories made any sense in fracture, or there's a lot of things always happening with metals, right? You have Hall patch effects. There's many things that happen in metals, and some of them are important. Small scale, some of them can be important for other problems, so you never know. So we decided to take a look. We first started using Quiescent sum models. This was before we looked into phase field. So I don't know if you're familiar with Quiescent sum models, but you can think of them as a glue, right? You have two pieces. If you know where your crack is going to behave, if you know that your crack, if you have some sort of geometry, and you know that your crack is going to grow in mode 1 along this line, you can put these cohesive elements here, and you can think of a glue. You're gluing these two parts with some sort of traction separation law, some sort of behavior that tells you how those two parts are going to separate from each other. And this is what you see here. So this is the traction. It is normalized. It's the stress divided by the critical strength, which is equal to 1 here. I pick a trapezoidal wall. It doesn't really matter. And this is the separation. And the energy, the area under the curve is the energy, the fracture energy. So in this case, because it's trapezoidal, my fracture energy is defined as this. These are some critical separation quantities. And then I can define two quantities that are quite relevant to the study. One is this is work I did, by the way, in Cambridge with Norman Fleck. So there's more details in the paper that we published there. But basically, you can define a reference stress intensity factor. So you know what is the relationship between fracture energy and stress intensity factor. So this is your definition. And then you can also define, based on the energy, every time you have an energy, you can define a fracture process zone, which in this case is defined like this. So Young's modulus multiplies fracture process zone, yield stress, and so on. So these are the two quantities that you normalize things with. And then if you do a dimensional analysis, what you figure out is that your R curve, so if you do a crack growth resistance curve, so basically what we're going to do is we're going to pull, we're going to measure the applied K, and we're going to measure the crack extension, and we see how these metals behave. And if you do that, you see if you do a dimensional analysis, what you find is that your prediction is going to be dependent on this non-dimensional quantity. So this is yield stress divided by Young's modulus, so a fixed number for a given material. This is crack extension divided by this fracture process zone. So this is a constant. This is a constant. Crack extension will evolve as the crack grows. This is the strength of your material, the strength of your Quiescent zone law, hardening exponent, Poisson ratio, some relationship related to the shape of your traction separation law. Those play a minimal role. And then you have this extra variable that comes from those size effects. And it's basically the ratio of the length scale to the fracture process zone. Because at the end of the day, what matters is the ratio of the length scale to your plastic zone, or your plastic gradients, or your fracture process zone. It's the same thing. They both kind of scale in the same way. If I have a very little load, then my plasticity is going to be very localized near my crack tip. My fracture process zone is going to be small, my plasticity is going to be small, and my gradients are going to be big. But if my load is very large, then my fracture process zone is going to be spread over a long time. My plastic zone is going to be spread over a high region, and therefore this guy is going to be small. So the length scale, remember, is a material property, it's fixed. You do these microscale experiments. And then how big this role will play will basically depend on this R0. And R0 will depend on the fracture energy. So if you have a material that is very ductile, this gamma 0 is going to be very large. R0 is going to be very small. Sorry, R0 is going to be very large. This term is going to be very small. And if you have a material that is very brittle, this is going to be small, this is going to be small, and this may start playing a role. This is what we wanted to answer. So this is the simulations. First, if we forget about crack growth, we just plot the stresses ahead of a crack. And we see, with conventional plasticity, you see here, your stresses are quite small, 3 times the yield stress. This is tensile stress ahead of the crack versus distance ahead of the crack. RP is the plastic zone size, the Irwin definition. But then we see, of course, that, depending on the value of this ratio, we get higher stresses. And that makes sense, right? So if your plastic zone is very large, then this ratio, the gradients are not going to be that large. Plastic zone is going to be widespread, and therefore this, assuming that you have a fixed L, then you're going to have a small ratio of this. But if your plastic zone is quite small, then you may have this big effect of the GNDs. The GND are going to play a big role, and you get a higher stress elevation. So then what we look is to this crack extension, so R curve. So we simulate the propagation of cracks, and you can see this is the, as you expect, cracks initiate when your applied K equals your toughness. Remember the definition. And then your cracks propagate until you get what we call the steady state fracture toughness, where basically your crack just grows unstable. You stop dissipating plasticity. And this is the result that you get for conventional plasticity, so you assume the length scale is equal to 0. And then for a fixed length scale, then you can change your gamma 0, and you can predict different R naughts. And remember the relationship between gamma 0 and K. So you can think of R0 also to be a function of the fracture toughness. So a very ductile material will have a very big K0, a big R0, and therefore for a fixed L, you will be somewhere here. So, okay, it may play a role, you'll be somewhere here in the top, a very small value of this guy. So maybe you play a role, or maybe what you get with conventional plasticity is also fine. But for a brittle material, you may be somewhere here. So maybe it's playing a role. You get much less plastic dissipation. So now what we do is we basically take the steady state fracture toughness, so the value here, when you reach this kind of horizontal plateau, and we plot it as a function of, because all these results are obtained for a given strength, fracture strength, 4 times the yield stress. But at the beginning, our first discussion was, okay, we see brittle failure when the strength of our local interface is 10 times the yield stress. How can this possibly be? So we're going to change this number in our calculations, and we're going to run calculations and obtain values of a steady state fracture toughness. And this is what you get. So first of all, if you look at plasticity, this is a steady state fracture toughness normalized versus the strength. Of course, because in plasticity my stresses are never big enough. They're always, as you see, they saturate at 3-4 times the yield stress depending on your hardening. You can see that your kind of failure surface or your fracture curve never really gets anywhere in this regime. So this is what we were discussing from the beginning, right? If my theoretical lattice strength or my grain boundary strength is somewhere here, we cannot understand this with conventional plasticity, because I can see that my conventional plasticity curve does not cross with this line. So this is what we don't understand. But when we put the gradient effects into it, you can see that, well, depending on the ratio between this L and R naught, then you may actually get a curve that tells you that fracture will happen, even when you have an interface with a strength is large. And now the question is, okay, will it happen or not? Is this a sensible value for any problem or not? So whether it will happen or not will depend on the value of L. This is a material property, a constant. We cannot play with that. We just do a test, and we fit it. And we know that it has typical values of 1 to 10 microns. Depends on your material, but 1 to 10 microns. And then will depend, of course, on the magnitude of the toughness or fracture energy through R naught. So a very ductile process, if we have a very ductile process, R naught, this guy is going to be very large, this guy is going to be very large, and we're going to be somewhere here. So no way it's going to happen. But what if we have a sufficiently brittle zone? And by the way, before I put in some numbers into it, I should say this is exactly what they see when they do discrete dislocation dynamics. So if we go down the scales, these kind of problems are difficult to solve with MD or DFT, but you can solve them with discrete dislocation dynamics. And with discrete dislocation dynamics, they see exactly the behavior. You can see here. So discrete dislocation dynamics will be something like this, I guess. It's 10 times, you see the curve. So discrete dislocation dynamics will correspond to a curve, but it's somewhere like this, basically.
A quick question. So you were showing the R curves earlier, effective size. Can you comment about the GC in each of these cases?
Yes. So in these calculations, we left the GC. So by the way, I should say, this is a very good point. I don't know why I use different notation. I guess because I wanted to mimic the acquisitive zone community. But gamma 0 is effectively GC. So every time you think about phase field, this is GC. This is your fracture energy. So whether we call it gamma 0, I think in the acquisitive zone modeling community, they used to call it gamma 0, but this is effectively GC. So this is remain constant, and it's fine because we're normalizing. So all of them, they start at 1. But of course, this is going to play a role. So here we are changing the length scale, but everything, if you do a dimensional analysis, again, is, remember when you do a dimensional analysis, this means that I'm going to get the same results if I keep these ratios the same, right? So whether I change, if this is 3, it doesn't matter that I change this value or that I change this value. I did dimensional analysis, I'm going to get the same answer. So you can get these curves. You can get these curves either by changing the length scale or changing R naught. You're going to get the same result because of
propagating, the resistance towards crack, the toughness of the material is decreasing, and the slope of that should, in essence, so GC in principle shouldn't be constant.
Yes, so actually, this is a good question, and I think one of you asked me that in the break. And I remember once I presented this to industry, and they raised exactly the same question. They were very puzzled. If you do a fracture mechanics test, J versus delta A, the experiments will look something like this. You get something like this. So eventually you saturate a little bit, but it looks something like this. So everyone doing experiments, they always think, okay, my fracture toughness is not a constant property. My JC0 it is, and sometimes they define at 0.2 some sort of J1C or JC. Those are constant properties, but if you think of subcritical crack growth, this is something that evolves in time. However, the way I prefer to see this is that the fracture energy is actually a constant quantity. So what happens, so if you had a purely linear elastic brittle material, what do you see? You see the cracking initiates here, and just, it's unstable crack growth. The crack just grows here. So what happens between here and here is plastic dissipation. Or if you have, a carbon fiber reinforced polymer composite, then you will be the bridging of the fibers of the crack. So there's a toughening effect coming from plastic dissipation. So anytime you run a cohesive zone or phase shield model, you capture actually the toughening, because that comes from the bulk, doesn't come from the interface, from the cracking. So in the cracking, you could keep your GC constant. In this cohesive zone model, the gamma 0 remains the same. Or in phase field, you keep your GC constant. But your model will naturally predict this thing. We saw some R curves when I was talking about, for example, the pipelines and so on. Your model will actually predict this thing because this is the plastic dissipation that is happening in the bulk. So I think that it is more kind of an extrinsic effect in that you have a fracture energy that remains the same, but you have a toughening effect as a result of plastic dissipation. And the model will capture that. So you don't need to put and I think this is one of the beauties of the model, because how big your plastic dissipation is might not be the same in a practical component than in your fracture test, because in the practical component, maybe your plastic zone is limited by the dimensions and so on. So the model will capture that. Capture the fact that you may get less or more plastic dissipation, more or less toughening in a component where maybe plasticity is a bit constrained relative to a big sample that you do in a lab test for fracture mechanics. So this is, I think, what is nice about these models is that without you having to tell how K evolves in time, or J, these things are captured. So you just pull, you measure your applied K, and you see how it's changing. You measure your load, exactly like an experiment. In an experiment, you measure your P, you relate your load to J, so you can relate your load to K, and then you see how these toughening effects come to play.
One final.
Of course.
So the plastic zone is rarely spherical. It's actually highly anisotropic. If you were to think about it, the length scale that we're associating with the plastic zone, are we taking the largest value from the practice, or are we?
Yeah. So the plastic zone will normally look, if I think of isotropic material and so on, will look something like this typically. I mean, it should be symmetric, but it looks something like this. So whether you take this or that, and I think here I'm normalizing by the Irwin plastic zone, that is this one here. So this will be typically if I have it here. This is what Irwin conducted as a plastic zone. When Irwin did these things before finite elements existed, when people started doing finite elements, they realized that the Irwin plastic zone was more or less an approximation. I think in reality, the Irwin plastic zone will correspond to something like this. In reality, it's a bit smaller if you think ahead of a crack. But in any case, sort of everything scales in the same way. So everything kind of scales proportionally. So it's an indication of how big your plastic zone. I'm not measuring per se the plastic zone. It's just a ratio of some sort of plastic length measurement versus my.
That's the length scale that's going into gradient plasticity.
Yeah, so the length scale going to my gradient plasticity is a material property that tells me how, in the presence of gradients, how much hardening happens in that material. But it is true that is whether the effect is big or not is relative to those, plastic zone and gradients of plastic strain. So how quickly the gradient, which scales with this, of course. So yes, this is so I guess it's an indication more or less of the number. Yeah. So yeah, this is what we get basically, and this is, by the way, what they see in discrete dislocation dynamics. So this is the idea. So things seem to make sense basically, and so now we try to apply this to see if we can understand those fracture phenomena that I told you before that people have seen in the labs on the multiple occasions that they get, basically that they get cleavage fracture in the presence of plasticity. So again, just to remind you, we cannot understand cleavage fracture in the presence of plasticity because stresses are not big enough. So now we see that, both in agreement with discrete dislocation dynamics and strain gradient plasticity, it might be that under certain conditions, if your fracture energy is small enough, due to the GND effects, you may get stresses that are big enough to rupture some sort of brittle interface. So this is what we look. The first case that we looked at was some famous experiments done in Germany on niobium sapphire interfaces. So they have this 4-point bending. We have alumina. We have niobium here, sapphire, and single crystal niobium, polycrystal and single crystal. And they measure very significant plastic work. So they have a crack, by the way, at the interface between the sapphire and the niobium. And you can see, by the way, just to emphasize a point that I said at the beginning, metals under normal circumstances fail in a ductile whale. We never get these funny stresses. Because basically, this K0, this fracture energy is very large, and therefore, R0 is going to be very, very large, and this is going to be very small, so we're never going to break that interface. We're going to be somewhere here. But there are occasions where we see those things happening. These are exceptional occasions, but these are the exceptional occasions that we're hoping to understand. One of them is this crack, and you see this is unusual in the sense that you have an interface. So the crack is growing in the presence of, it's seeing a lot of plasticity on the left, but then it has a brittle material, a ceramic on the right. So they measure significant dislocation activity, significant plastic work, but they show cleavage fracture with an atomically sharp crack and very clean fracture surfaces. And there's a lot of people who have been working on trying to understand this. The group of Sigan Suo in Harvard has a model called the SSV model to try to understand this based on some ideas based on dislocation-free zones and other things. We try to understand with these gradient models. And what we did, this is one of the gradient models where we simulated exactly those conditions. And what we saw is that, at the critical load at which they saw failure, the result with conventional plasticity looked like this, but the distortion, the gradient plasticity model gave you a stress elevation that it was something like this. So you can see that, under those conditions, it seems, and one key point here is what happens at the interface. We had to use a higher order gradient plasticity model because you need to block dislocations, emissions, or you need to block dislocation transport or dislocation going from the niobium to the sapphire. That's also important. But when you do all of these things, you see that your stresses are large enough over a sufficiently long distance. You need 10 times the yield stress. Okay, you get 10 times the yield stress here over a micron or so. So that's arguably probably enough to rupture this. So it seems to be explaining these things. It seems that basically when we put the right L and the right L0, the stresses are not here as they will be. In this case, they are more or less somewhere here. So this seems to explain this, what happens here. And in fact, then we plot dislocation densities and we compare with some synchrotron measurements. This is the Nye tensor, and we can see that the densities that we get on the Nye tensor seem to be on the same order of magnitude that they're seeing in the synchrotron. So it seems that it can explain this. The other problem is low temperature cleavage. So ferritic steels, they will fail under cleavage under low temperatures. And usually this is described using Weibull type statistics, so what people call the Beremin model. It's a cleavage fracture model, and it's based on some principal strains. But we have models out there that explain how it works, but we don't really have a mechanistic interpretation because at the same time, how can it be that these cleavage-like features, these interfaces are rupturing when my stresses are not large enough? So this is the problem. So how do we explain this? And what we saw doing this kind of Weibull type of statistical analysis is that we can build these hazard maps where we can see the probability of failure, and we can see, so with these kind of Weibull models, you can predict this cleavage fracture even if your stresses are not big enough because you average things, you fit some parameters, and everything washes out, and you can predict this brittle fracture. But these Weibull type of models will also tell you the region over which you get a probability of failure. And when you have conventional plasticity, we have regions of failures that are on the order of 10 millimeters, while with gradient plasticity is on the order more like 100 microns. And when you look at the experiments and you look at the critical distance for cracking, you can see it's based on inclusions, and people have done very careful observations of fracture surfaces and so on. They typically report between 20 and 100 microns. So it seems that this seems to makes much more sense. So this seems to explain as well this kind of low temperature cleavage. This is a bit of the details of the 3-parameter Weibull step that we had. And then just to go back to hydrogen embrittlement, again, we are interested in, can we understand hydrogen embrittlement based on this? Because, and we discussed this during the seminar, if you ask some of the people working with, other plasticity-based mechanisms, they will tell you, the problem with this, the cohesion mechanism is that, yes, you look at the grain boundary, you see that has broken, but I cannot explain it because in order to break a grain boundary, you need stresses like this, and they're thinking of conventional plasticity, say the gap is simply too large. So would it be relevant as well? So it seems that it can explain, the cleavage fracture in B materials. The stresses seem to be in the right order. It seems that it can explain the low temperature cleavage as well. The statistical analysis shows, surface regions or failure regions of the order of what we see in experiments. And then what happens with hydrogen embrittlement. And again, what you see, the hydrogen embrittlement effect is twofold, because having higher stresses is not only relevant to, achieve your stresses that you need, but it also increases your hydrogen concentration. So that's important, because then, that degrades as well your atomic bonding strength. So sometimes if you think of, from an atomistic perspective, when you go to that graph and say, what is my coverage of my interface, your concentration is going to be very large near surface. And this is what people have measured, basically. I think if I have it here, people are measuring very large hydrogen concentrations near crack tips, and only when you account for the G and D effects, you can capture this. So that's already, a point in the right direction, but let's see if this matches. So this has moved a little bit, the slide, I don't know what happened, but anyway, this is the point. So a reminder of what we have. So this is an inert environment. I'm running a calculation here where I'm doing again the same thing as before. So this is the steady state fracture toughness versus the cohesive strength. For brittle fracture to occur, my fracture line has to cross this black line. This is the brittle fracture line. When I have ductile fracture is when I don't cross that line. I need other mechanisms to occur. So if I don't have hydrogen, that's what happens. If I bring hydrogen into the picture, what hydrogen is doing is reducing my fracture energy. This we see in experiments, right? We do fracture tests, and we see that hydrogen reduces your fracture tests. So fracture is going to happen at lower loads. Fracture is going to happen for fracture process zones that are smaller, for plastic zones that are smaller, and therefore where gradients are going to be larger. And again, this is also what they see in atomistics. This is the kind of traction separation law that they see in atomistics as they increase the amount of hydrogen. You see there's a degradation there. So basically what you have is that you have a fracture energy that depends on the hydrogen concentration, and therefore your R0 is going to depend on the high concentration. If you have a lot of hydrogen, failure is going to happen at a very low applied load, at a very low toughness, and therefore a very low fracture process zone, a very low plastic zone. So gradients are going to be playing a big role. And this is what you see when you put 1 ppm, for example. So all of these lines have crossed to the right. So even if your length scale is such, the length scale of your material is such that you are somewhere here, now with hydrogen, which is normally the case, normally we have ductile materials where somewhere here the length scale is very small, it's on the order of microns. My R0 is quite large. Hydrogen has suddenly pushed all this curve to the right. And this is important, of course. And I think I had some slides on this, but maybe I don't have them. I'll tell you what happens when you have gradient plasticity here. So this is for conventional plasticity. What do you get when you get gradient plasticity? Well, with gradient plasticity, you always get this stress elevation near the crack tip. So even for small loads, you will get a stress that is quite large. You saw it, I think I showed you before. Let me bring back that figure. This one, for example, or this one. Huh? You always get very high stresses, but they are very localized. And remember, for a crack to grow, the stresses need to be large over a critical distance. You need an energy. So gradient plasticity will tell you, if we look at the lowest load, your stress will be like this. Okay, that's not big enough. So let me rephrase this. What we think is happening is the gradient plasticity picture is the most precise. It incorporates an extra ingredient of physics that we see in experiments that conventional models do not have. So this is what we all trust and believe. But what happens with that? Okay, it's still metals fell in a ductile well, so something needs to happen. So in a metal, I start loading like this, and then this is what I get. And then, how big the elevation will be will depend on L divided by R0. So it depends on your length scale and so on. But, you get for any material, you start loading this thing. And then normally metals, you get something like this. Sometimes eventually with gradient plasticity, you see when you do large strains, you get a drop eventually. So all of these things are high enough, but they are not high enough over a sufficiently long distance. So I need something else. I need microvoids to grow and coalescence. Otherwise, I cannot get failure. That being said, what happens when you get gradient, when you have hydrogen, for example, or this kind of, a brittle material ceramic interface. The ceramic interface basically blocks dislocation emission, so you get a little bit more of stresses. In low temperature cleavage, you lower a little bit your fracture energy. When all of those things happen, basically this thing goes down. So now this curve is going to be big enough. But if you don't get failure, this continues to evolve like this. And it starts to go down at some point because the plastic, the strain gradient effect will become lower and lower as your plastic zone increases. So if you don't get failure at a certain loads that are low enough, then this thing washes out. So that's why then eventually everything becomes dominated by gradients. But it could be that if something exceptional happens, that thing gets lowered a little down and it falls within that regime. This is what we believe. Or this is what we see with these kind of models. So a critical question, of course, is also when it comes to hydrogen embrittlement, what is the critical distance of the problem, right? So if I take you back to this theory, so this is the hydrogen concentration that basically resembles the hydrostatic stress, or maybe it's more clear in this one that I was showing you before. If my fracture mechanism occurs at a high distance ahead of the crack tip, if I'm somewhere here, if I'm at a millimeter ahead from my crack tip, then actually those gradient effects, those GNDs are not important, because GNDs are very localized. The effect is very localized. So it matters for everything that is localized. If your fracture process is happening far away, then it's not important. So the key question in hydrogen is, okay, where does fracture happen in hydrogen, right? What is the critical distance of the problem? And I think in any problem that you're looking at, in any engineering problem, you always need to think of what are the critical variables of my problem, and what is the critical distance over which I need to map these variables. And the critical variables of hydrogen are your stresses, effectively, and your hydrogen concentration. I mean, you can think of energy as well, but that comes from stresses. So it's basically a mechanical term. Think of crack tip stresses, and a hydrogen concentration term. Whether you have a lot of hydrogen, a little hydrogen, whether you have a big load or a small load, this is what matters. So stresses and hydrogen concentration. And what do I care about? So of course I always want to predict things at the large scale. We want to serve society. We want to serve engineering practice. So continuum level is ideal for us. But of course we want to have physically based models that are reliable and therefore depend on resolve the physics of the problem. So if all the physics of your problem are happening in the first 3 atoms ahead of your crack tip, then you need atomistic resolution, and therefore you're a bit screwed because there's no way you can resolve the large engineering component with atomistic resolution. So the question is, where are we in hydrogen embrittlement? What is the critical distance to the problem? And that you can figure out from experiments. Because as you can see here, hydrogen embrittlement is a little bit like you see in fatigue sometimes. So if I plot, this is the crack velocity versus the stress intensity factor. In hydrogen embrittlement, you follow these 3 stages. You have a stage 1, where your crack velocity increases quite a lot with applied load. So this is an experiment where I'm increasing my applied load, so I'm increasing my stress intensity factor. I increase my applied load. You see we have a stage 1. My crack speed is growing quite a lot with the load. Then I have a stage 2, where the crack is actually not growing that much. It's the same crack velocity. The crack is growing, but at the same speed. And then finally I get the final rupture. And you see here experimental data for various materials that kind of follows that trend, basically. So this is what we see all the time in hydrogen. So why is this, you may wonder? Why we have a situation where I keep increasing my load, there's more energy coming in there, my energy release rate is growing, but my crack speed remains constant. Why is it this? And what you see in the experiments is that what happens is that the crack is kind of jumping. So you initiate a crack, and then boom, it jumps for a certain distance, and then it jumps a bit again, and then jumps a bit again. So this kind of interrupted cracking process is basically diffusion controlled. So even though we're increasing the load, the crack is not growing because for the crack to grow, it needs to wait for the hydrogen to, so let me put it here. So you have a crack here, and then eventually you see that the crack has jumped here, and then it has jumped here. But for the crack to grow here, the crack, even though I'm increasing my load, is not growing because the crack needs to see embrittled material in front of it. So the crack needs the hydrogen that is here to enter, to travel to a certain distance, and then embrittle my material. Maybe you have a grain boundary or an inclusion, something there, and then your crack grows, and then you need the same process. The hydrogen has to go there. So even though I'm increasing my load, even though I have more stored energy, the fracture toughness that I see is quite large. I cannot grow. I need to wait for the hydrogen to go and embrittle my material. So the rate limiting step is the hydrogen being transported to this critical space. So that's good because we can use experiments to determine what is the critical distance at which, if experiments will tell me how long do I have to wait, what is the critical distance at which hydrogen happens. And you can see an example here. So this is for nickel superalloy, muon LK500. And there's two things that you need to pay attention to. First is that, there's an analytical solution for 1D diffusion. I mean, in reality, diffusion is also influenced by hydrostatic stresses, but for illustrative purposes, this is good enough. So a distance that a hydrogen atom travels d is equal to 2 times the square root of diffusion coefficient multiplied by time. So this is going to be my distance d, or you can also call it x crit, the critical distance. And how long it will take to fulfill that will be 2 times the square root of diffusion coefficient of that material plus t. So if it's a material that where hydrogen diffuses very fast, then it will travel faster, and then depends on the time, of course. And then the other thing that we know is that we can measure the crack speed in this stage 2. So this is what I'm plotting here. Crack speed in this stage 2. So this is this crack speed, this intermittent crack speed, stage 2 crack growth as a function of applied potential. So this is an experiment where you here have hydrogen embrittlement, here you have very ductile failure. So if you look at, for example, these 3 replicate points, where we get very good repetition, we get that this dAdt is 0.04 microns per second. So then if you think of crack growth, basically you have 2 algebraic equations to solve. You have an equation that tells you, the hydrogen is moving a critical distance jumping, my crack is going a critical distance 0.04 microns over whatever time is critical, and then you take this diffusion equation, the critical distance the hydrogen will take to travel that critical distance. We know the diffusivity of the material, in this case is 0.01 microns to the power of 2 per second, and the critical time. So, a simple system of 2 algebraic equations, you solve, and what you get is that the critical distance is 1 micron. So fracture, that crack is jumping, this distance is 1 micron. So those effects that we saw before, those gradient plasticity effects that we saw before, they're going to play a big role, because the critical distance on this problem is 1 micron. If it was 10 millimeters, then it wouldn't matter, but because it's 1 micron, it matters. So again, we need to consider those gradient plasticity models. You bring those into the picture. You see that the stresses are big enough. Yeah?
The slide you were showing the crack in the 3 stages.
Yes.
Yeah, the first curve, it's typically for a stress corrosion cracking type of phenomenon, right?
This is for hydrogen embrittlement as well. So yeah.
Sustained load cracking, are you talking about that?
Or rising load experiments as well. You get some sort of subcritical crack growth.
Constant load type of test.
Or increasing load type of test as well. You can also see an increasing load type of test. Yeah.
But in these type of tests, generally the K1 which is being set, it's around like 25 MPa root over meter or something like that.
You mean the KTH or the K1C?
Experimental K, I'm talking about.
You mean the K, this K or this K?
At the plateau K.
Here, this K.
Yes.
Okay, in this case it's more like 60, yeah. Yeah.
So, like the basis, because this cracking phenomena is like a stable crack growth,
Yes.
okay, occurring in a intermittent way.
Yes.
So, but when we are carrying out tests in a monotonic loading,
Mm-hmm.
so do we get sufficient time for like hydrogen to come, form this, and then crack to like these two?
Depends on your loading rate, of course. Depends on your loading rate. But these are experiments on hydrogen. This is this is cathodic protection. This is purely hydrogen embrittlement. These are rising load experiments, and we're measuring the dAdt2 crack speed. So these are experiments done by the group of Gangloff in Virginia. So this is so it's a typical experiment, I would say, in hydrogen embrittlement. You don't pre-charge your sample, so you're very dependent on the hydrogen coming from the environment. So it's environmentally assisted hydrogen fracture. So you don't pre-charge your sample, so you're very dependent on the hydrogen. That's why you see this very clear stage 2, where you need the hydrogen to diffuse. Otherwise, you don't get any fracture. Yeah. So it's subcritical crack growth because your sample has not been embrittled in a way. It needs the hydrogen to come in and embrittle. Yeah.
Only one small clarification in this expression. The d that you have, the small distance as a function of 2 times the square root.
Yeah.
When you said that I have in possession the minimum crack growth that I have per delta T in monal, that's the value that you are saying that the crack would grow after every time step that you look at the experiment, right?
Yeah, so it's kind of this intermittent crack growth. So the crack jumps at distance A or X over a time T. Yeah.
Delta T or let's say.
Yeah.
If I look at it from another perspective, is it correct to say that in the time frame that you are looking at it, accounting for the diffusivity of hydrogen, hydrogen is actually capable of moving 1 micron? Is that the correct way to see it?
Yes, yes.
So even though based on my crack velocity being 4 × 10⁻⁻2 microns per second, my crack is only growing roughly 120, almost 1/100th of that, right? Hydrogen is able to move 1 micron, right?
So it depends what you consider your critical time, right? I haven't got an expression here for the critical time, but so this jump is not happening. So this intermittent jumping is happening after a critical time. So you need to. So it's not happening every second or whatever. It takes some seconds for the crack to jump. So I guess in this case we have 0.04. So yeah, it takes maybe 20 seconds for the crack to jump or whatever it is. So then basically you combine this with these gradient plasticity ideas, and then the idea is that at 1 micron you do have stresses that are big enough over a sufficiently long distance. And this is what I wanted to connect with the story of yesterday. This is the part that I want to finish with the hydrogen. Maybe actually we can do a 5-minute break now here, because this is, well, I'll finish this, and then we do a 5-minute break. So the idea is that we have this situation where yesterday I told you hydrogen is lowering your fracture energy, your surface energy. How much it lowers depends on how much hydrogen you have. We know that in some interfaces hydrogen likes to accumulate, like grain boundaries. So hydrogen is going to lower my fracture energy. And then the other aspect that we know is that our cleavage strength is going to be a bit lower by hydrogen, and this is difficult to understand in the context of plasticity because still the jump is too big, the difference is too big. But when you account for those gradient effects, your stresses are large enough, and these two lines cross. This is the idea. So basically, you have a model that can capture in principle or provides a mechanistic interpretation of what is happening there. Okay, I have 2 case studies to discuss with hydrogen, but I think we can do a 5-minute break now. So until 10 past 10. Any questions? Any extra questions? No? Okay. Oh, there are some questions, yes.
Again, I'm a little bit stuck on GC, but in all these simulations, is GC a function of the hydrogen concentration? Or
So in these ones that we showed here, in these ones, no. This was a study in general where we said about all brittle fracture processes will somehow lower GC, but we don't know. We're going to make things without knowing how much is lower. Just then you need to put in the numbers and say, if I put here the right number, is this R0 low enough that I'm in this plot, or am I somewhere here, and so on. In this one here, we run these calculations. We realized that for a ductile metal, we were somewhere here in this purple line. And it's a pity I forgot to include the slide where we actually put the numbers. So you can put the numbers and see that you're actually here based on the typical length scale of plasticity and the typical R naught. And then now we had a graph of GC, gamma naught or GC versus hydrogen content. We put 1 ppm, and we saw that all of these things move to the right. So in a way, because you lower GC, you lower R naught, your gradients become very large because fracture precision is small, plastic zone is small, and then our stresses were big enough that we could see this. Ideally, interfaces break. Yeah.
The hardening, the hardening due to the lower length means the small L. So it was not there due only for the uniaxial test.
Yeah, because the uniaxial test has no gradients of plastic deformation. The stresses are uniform, so there's no non-homogeneous plastic deformation. It's all uniform. You need the gradients, you need the spatial variation of plastic strains to see this GND effect. So GND are dislocations that need to be geometrically necessarily accommodated. So you need to have a gradient of plastic deformation to fix them in. Otherwise, they don't exist. This is a good point. So it is true. If you look at the microscale in a polycrystalline material, you will see, and people discuss quite a lot whether For example, Hall patch effect could be related to this because they say, you have within the grain, you have gradients of plastic deformation. They're not going to be very large, but there will be some sort of gradient effect, so they could play a role. Yeah. Well, you do see some. So, I mean, the problem is that they're not very big, those gradients. So they kind of wash out at the large scale. But if you look at Hall patch effect, so things when you change grain size and so on, that you make those gradients. So, for example, you could argue I have a gradient of deformation within my plastic zone. But this gradient of deformation within my plastic zone, within a grain you have a plastic zone gradient. If your grains are big enough, it's going to be small. But as you bring your grains, make them small enough, then you're going to have this. So sometimes there's a grain size effect, and people argue that this. So maybe this small difference is actually due to that. You have some sort of small grains and some sort of macro scale gradients, but normally they're small compared to what you get in torsion in a thin wire, where you have this big change in plastic deformation.
Case of bending, we'll see the skillet, right?
You do see it, yeah. In bending, so if you start bending thin foils, I mean, there's a lot of people that have done experiments on very thin foils, on nickel and other materials. You see thick foils, no problem. You start lowering your thin foil, then you see this. If you normalize the moment, you get a very racing moment eventually when you get to very thin. Because you need to accommodate, you have gradients of plastic formation, you need to accommodate those GNDs. Yeah. Okay, maybe we'll do a break. So 5 minutes from now, so. Okay, let's say 1/4 past.